Math 1314, Tyler Junior College. Section 3.5, Rational Functions. Graphing via the 7-step approach, example 2. Yeah, this is a junkier function. But I was thinking about how many videos we've already made for this series. We are currently on 1, 2, 3, 4, 5, 6, 7, 8, 9. We're on video 11. And I still got 2 or 3 more planned. So I'm going to try to kill a couple of birds with one stone. Hence we have a junkier function. F of x equals 6x squared over x cubed minus 4x. The point I wanted to make on this one, before we go through the 7 steps, is you may have a function that has a different reduced form. So prior to all this, what you should actually do first is try to reduce the function, because it will save you some headaches if you try to reduce it now instead of waiting until you look for vertical asymptotes and holes. But before we do this, we should also actually try to identify the domain. So if I had to reverse this series of step numbers, this would be step 0, this would be step -1. So what's the domain on this one? Well, for the domain, we would need to solve x cubed minus 4x equals 0, which looks tricky because it's a cubic equation. But a quick observation, you'll see that there's a common factor of x. And upon factoring it out, you get x times x squared minus 4. That's a difference of squares. You get x times x plus 2 times x minus 2, which means there are 3 numbers excluded from this domain. X cannot equal 0, x cannot equal -2, and x cannot equal +2. Now, it's not a bad thing that we find the domain first, because when we go looking for the vertical asymptotes and holes, we were going to have to solve that anyway. So we've already done it. Now, let's talk about finding the reduced version of this function. I'm going to put quote on here. Well, it's technically, it is equal now. It won't be equal after we reduce it. We already know what the the denominator factors into. It was there and I just erased it. But the denominator factored into x times x plus 2 times x minus 2. The only factor we can cancel is this x with one of them on the top. So the reduced version is 6x over x plus 2x minus 2. So let's go ahead and make a note of that here, that the reduced function is 6x over x plus 2x minus 2. Let's put it back. Let's refoil this and call it x squared minus 4. So if a function reduces, you'll want to reduce it at the beginning. Then begin your analysis after you find the domain, or rather the domain's exclusions. All right, so let's check even versus odd. Which one should we do this on, the original or the reduced? The answer is on the reduced. If we want to check even versus odd, so for the even-odd discussion, we start by calculating f of -x, but we're doing it in the reduced function. So let's just talk it out real quick. Putting a negative on the top gives us -6x. Putting a negative here gets squared, so it disappears and leaves us with x squared minus 4. This is not the original function. It almost is, except for that extra negative. But original reduced function. But because of the extra negative, I now know that the negative of the reduced function evaluated at -x. If I just take a negative on this fraction, I can give it to the top, make the 6x positive, and that's equal to the original reduced function. Because negative f of -x equals f of x, reduced. This is an odd function. Therefore, odd function, therefore origin symmetry. So this graph will have origin symmetry, meaning the left half is a rotational image of the right half across the origin. Y-intercept. For the y-intercept, we substitute 0, but we're not going to.
Why not? Very first thing we did. There were 3 values excluded from the domain of the original function, and one of them was 0. So when it goes to the intercepts, to the y-intercept, use the original. F of 0 is undefined. And to be honest with you, you should use the original function for the even-odd discussion. I'll tell you right now, the only difference between the original function and its reduced version, the only difference in their graphs, the reduced one might have a hole in it. Excuse me, the original might have a hole that the reduced one didn't. Everything else is the same, asymptotes, intercepts, etc. But wait a minute, we can put 0 in here. What does that mean? We'll find out in a minute. X-intercepts, we have to solve the function equal to 0. Notice I wrote original function. What does this imply? Well, the only way a fraction can equal 0 is if the top is equal to 0, and if we put 6x squared equal to 0 and solved it, that would give us x equals 0. So there seems to be an x-intercept at x equals 0, but what's the problem with that? 0 is still excluded from the domain. So no, there is no x-intercept. But I can put 0 into here. I know. Bear with me. Now let's have the vertical asymptote and whole discussion. Remember how that went. You solved the denominator equal to 0 and got the values that are either asymptotes, vertical asymptotes, or wholes. But to pass judgment on who is whom, you go to the reduced. If I put 0 into the reduced function, I'll get 0 on top, but I'll get -4 on bottom. That's equal to 0. If a number makes the original function undefined, but the reduced function is defined, that means hole in the graph. And not only does it mean hole in the graph, I know exactly where it is, at 0, 0. Oh, the reason we kind of had a y-intercept but didn't, and kind of had an x-intercept but didn't, is because there's a hole there. As for the other two, if I put 2 and -2 into the reduced function, they still make the denominator 0. Those are undefined. That means that there's a vertical asymptote at x equals plus and minus 2, which I'm going to write lazily as x equals plus or minus 2. So the reduced function role is to identify a hole in the graph. And I'll tell you right now, if you ever have a discrepancy with intercepts, I think there's a y-intercept, but it works here but not there. Or I think there's an x-intercept, but it works here but not there. That usually means there's a hole. All right, so we have a hole at the origin. Horizontal asymptote, we can answer that with either version of the function, original or reduced. All we have to do is compare degrees, but in both of them, the degree of the denominator is greater, and that means that the horizontal asymptote is y equals 0. Let's sketch what we have. No intercepts. We do have a hole at the origin. Everything that was trying to be an intercept couldn't be because of that hole. We have a vertical asymptote at 2 and -2. Or rather, I should say we have 2 vertical asymptotes. One at 2, one at -2. And we have a horizontal asymptote at y equals 0. That's also known as the x-axis. We don't have a lot to go on. We just got a hole that the graph tries to go through. We need a lot more evidence. So here's an example of where we need so much more evidence. Now, do we use the original or the reduced? The reduced, because the only difference between the original functions graph and the reduced functions graph is possibly a hole, or there could be more than one hole. So as long as we don't try to substitute the values that created the hole, which we won't, because we already know what happened there, we will get points that belong to the original functions graph. So it doesn't matter if we use the original or the reduced here. We'll use the reduced because, well, it's reduced. But what are we going to plug in? Well, I don't know anything to the left of x equals -2, so I need some evidence to the left of -2, like at -3. I may need more evidence, we'll just start there. I know what happens at x equals 0, there's a hole, but I don't know what happens in between, so let's get some evidence between -2 and 0, that would be at -1. And the same thing over here, I don't know anything between 0 and 2, so let's see what happens at 1. And I don't know anything to the right of 2, so let's see what happens at 3. So it looks like I'm going to get 4 more points, and notice I said looks like. I don't need all 4, I can just use 2 because of the origin symmetry. Remember, one way to think about an odd function is opposite inputs produce opposite outputs. Opposite inputs produce opposite outputs. So if I know the outputs for the negatives, I just take their opposites and get the positives, or vice versa. Let's do the positives. If I put 1 into the reduced function, I'll get 6 on top. 1 squared minus 4 is -3. I'll get -3 on bottom. 6 divided by -3 is -2. If I put 3 into the function, 6 times 3 is 18. On the top, on the bottom, I get 3 squared is 9, 9 minus 4 is 5. So I get 18 over 5, which doesn't reduce, but I can divide it and get 3.6. Now I can substitute -1 and -3 and get their answers, but again, being an odd function means opposite inputs produce opposite outputs. So since 1 and -1 are opposite inputs, their outputs will be opposite. This output is 2. And the same thing with 3 and -3. This output is -3.6. Substitute them if you don't believe me. Or substitute them if you don't want to have to think about, oh, it's an odd function. Let's plot these dots and see if we can get a graph. -3, comma -3.6. -3, -1, 2, 3, 4, so it's going to be way down here somewhere. Probably about there. -3, comma -3.6. -1, comma 2, back 1, up 2. 1, comma -2, 3, comma 3.6. It's about there. This doesn't look like a lot of evidence, but it's actually everything I need. On the right side of x equals 2, there's either a branch on the top or on the bottom. This evidence says it's up here. Now, can I get away with just sketching that? Well, actually, yes. Because we're not really looking for precision, we're looking for location. And it's located up there. I would have to draw a bigger graph to get more precision. Same thing on the left side of x equals -2. There's either a branch above or below. It's below because of this evidence. And again, using the same argument, if you will, I'm looking more for location than precision. In online homework platforms, usually this would be a multiple choice question. Choose this correct graph. If you're doing it by hand, you might want to get more evidence, such as putting in 4 and -4. Ask your professor. In the middle of the asymptotes, I need to go through this point, go through the hole, go through this point, and not hit, but approach the asymptotes. So I know the middle is going to look something like this. And if you're wondering, can you cross a horizontal asymptote? Actually, you can, because the role of a horizontal asymptote is to determine end behavior. It has no say about middle behavior. What about this? Should it go up or should it turn around and go down? It can't turn around and go down. It would have to have another x-intercept. The absence of an x-intercept means it can't turn around, so it has to continue going up. And the same thing over there. So when you have a function that can be reduced, reduce it at the beginning. But before you do, make note of the exclusions from the domain, because you're going to need those numbers when you're determining vertical asymptotes versus holes. If intercepts are acting goofy, it's probably because there's a hole. In fact, I would argue that you should find the asymptotes first. Because if there's something fishy going on at x equals 0, you'll find it here, so that by the time you get to the intercept discussion, you don't have to worry about what's going on with the intercepts. So if I invented math, and if I ever refilm this, I will reorder this, I would locate the asymptotes before finding the intercepts, because that'll fix all those issues with, it's a hole in the graph, it's not a hole, it's an intercept, it's not an intercept. I got one more concept I want to show you and an example.